Bismillahirrahmanirrahim. By way of application of our knowledge, let's solve this problem. It's a very simple truss problem, two elements only. So let's solve this. This is the load given, just one load, and the area and material properties are also given. So let's start with labeling the nodes. 1, 2, 3. Doesn't matter which node you number what, but once you do that, we must be consistent throughout. Now, if I have to make use of the simplified formulas for calculation of L and M, then I must first decide my origin. It doesn't again matter which point do I consider as the origin. If this is the origin 0 0, then this is obviously 0 300, and this point is 600 0. So it doesn't matter. We could have taken this as origin and the result would still have been the same. So now we are in a position to use these formulas to calculate L and M. So we don't have to bother about thetas and then using trigonometry. Obviously these are also trigonometric relations, but they are basically the easiest to use. So do it any way you like, as long as you don't make a mistake, it should be all right. I'm just following what I think is the easiest way to do it. Now it always helps to make a connectivity table. We are going to use it anyway, but it's better to have it ready with us from the very start. Without this connectivity table, we'll not be able to assemble it properly. And when we make a connectivity table, it's better to include all the relevant information here so that you don't have to look at different places for that. Just get all the relevant data in one place. So it's always better to follow this. So element 1, element 2, the I node for element 1 is 2 and the J node is 3. The coordinates are 0 300. I'm just reading off the diagram. And for 3 the coordinates are 600 0. Similarly for element 2, the node I node is 1, node J node is 3. This has 0 0. The coordinates of this are 0 and 0, and the coordinates for this are the same. 3 is the same, so the coordinates are the same too. And now if I use these equations, I can get the length of each element. This element is 600 obviously, but for this I can get the length, and then I can get L and M. And in this case these things turn out to be 670.82, and this is 600, as is very obvious. This latter one is very obvious, and L is 0.89 and M is minus 0.45. Here it's 1 and 0, again very obvious. For a straight line it has to be 1 and 0. Now let's start from making the elemental matrices for each element. There's just two elements, so K1 will be AE over L, and then we have this again, this formula L square LM minus. For element 1 we'll use this. In this case element 1 and 2 both have the same, so you'll have the same K matrix for each, but that K matrix, the same K matrix will be only this part will be the same. These parts, these are constants, so this will be the same, but this 1 and 2 have very different values of L and M. So this part will be different, obviously. So let's start doing it using this. We get a E is 200. We convert usually it into MPa, and then we have the length is also different, 670.82. So this part is also different for the two. And the main difference, even if your material properties are and geometric properties are constant, the main difference is created by these values. Here you'll get 0.79, and the students are advised to verify these relations. This is the K1, and this will be in global coordinates. You must realize this. Otherwise, it would have been AE over L1 minus 1 minus 1 1. This you have converted it into this system. Now this turns out to be, and I think we can write it. If we simplify it, then this turns out to be should also, just to show that this is the global coordinate system, K0 1. Similarly, K0 1 turns out to be 5888.31 minus 2981.42 minus 5888.31 2981.42, and here all those checks you are familiar with, rows add up to 0, all that sort of thing. Please be mindful of those, because it's very easy to make mistakes when there are a lot of numbers involved. And then 588. So this is your K1 matrix. Global coordinate system, element 1. Element 2 turns out to be very simple, because it is just aligned in the for element 2, the local and the global coordinate systems are one and the same. So you should expect a very simple solution here. But again, the dimensionality will be the same. It won't be 1 minus 1 minus 1 1 type of system, because here you have 4 by 4, so you need to have a 4 by 4 system, and it will come out to be a 4 by 4 system just by following the formula that we have derived. Here we put in the values, 25 area, this is the Young's modulus, and then this is the length in this case element. And because L is 1 and M is 0, so we will simply get this sort of a system. And if you simplify this, 8333.330 0 0 0 0 0 0 and 0 0 0 0. This is your K2 matrix. Now it comes this time to assemble the two. So when we talk about the connectivity, element 1 is linked with node 2 and node 3, and element 2 with node 1 and 3. Now for 2D systems, because each node is connected with u and v 2, so first this one will have the degrees of freedom 1 and 2 for the whole system. This 2 will have 3 and 4, 2i minus 1, 2i, and third will have 5 and 6. So this is a, because it's a 2D system, there are 3 nodes, each node can move in 2 basically dimensions, u and v. There are 6 degrees of freedom. So degrees of freedom involved with element 1 are 3, 4, 5, 6, and element 2 are 1, 2, 5, 6. So just label, just for our own clarity, 3, 4, 5, 6, 3, 4, 5, 6. As far as element 2 is concerned, 1, 2, 5, 6, 1, 2, 5, 6. This is how you label them. And the K matrix for the whole system, that comes out to be, just now we are just going to put them in the relevant place. This 1, 1, this comes here. This is 5, 1. So it will come in this place, 5th place, and the first line. So we just take these here from here and then put them in the relevant places. This 3, 4, 5, 6, this is easy. This just comes as a chunk in the 3, 4, 5, 6 row and column place. But as far as this is concerned, you have to separate it into 2 parts. First row, first column, second row, second column, and then 5th row, 5th column, 6th column, 5th row, 6th row, 5th column, 6th column. So when we put the values, we get something like, and again the students are advised to follow and do these sums themselves and make sure that this makes sense. Zero zero minus 2981.42 1490.71 2981.42 minus 1490.71. Again, this was broken 1, 2, and 5, 6. So now this part comes 0.330 minus 5888.31 2981.42 5888.31 plus 8333.3. Here both combined because 3 and 4, there's some common things here, and here minus 2981.42, and the last row 00298.42 minus 1490.71 and minus 2981.42 and finally 1490.71. Now all these values are now in place except this. When you add them together, this turns out to be 14221.64. So this is your global K matrix. And obviously this is 1 2 3 4 5 6 1 2 3 4 5 6. Now this is your global K matrix. Now this has been assembled, so the next step is, obviously this is the K matrix. This is the matrix that I'm not going to write this again, but if this is the K matrix 6 into 6, then you have u1 naught, v1 naught, and we are talking about the global system, u2 naught, v2 naught, U3 naught, V3 naught. Now there are no temperature change involved here. Body forces, pressure forces are already irrelevant in these problems. So the only force that is being applied is this 1000 Newton force. So we just, because if there was a thermal element involved in these two, we would have made the thermal vector for each element like this, and we would have combined them together in assembly just like we did the K matrix. But now there's no need for that. So at the end we always take the concentrated loads, and that's what we are going to do now. The concentrated loads are nothing but element 1 uv direction fx fy 0 0, element 2 0 0, element 3 0 minus 1000, minus because it is acting downward, 0 0 0 0 0 minus 1000. Now can we solve this now? No, we can't, because we have to apply the boundary conditions. When you apply the boundary conditions, then obviously degree of freedom 1 and 2, with node 1 we have 1 and 2, with node 2 we have 3 and 4. 1 2 3 4 are 0. There is no displacement here. The only displacement possible are at u3 and v3. These are the three, fifth and sixth one. So we can simply, I'm just going to apply the boundary conditions here. This is 0 0. If this is 0, then this is r1 x naught, this is r1 y naught, again 0, plus r2 x naught, 0, r2 y naught. So in effect we are just left with this, because by elimination approach, if these 4, then we just eliminate first 4 and first 4 these. So we are just left with the last two elements, 2 by 2. We're talking about this one, one for this, and that means that u3 v3 are -1422 1.64 -2981.42 inverse, because this goes to the other side, and then it's very easy to take the inverse for this, and u3 v3, your calculator will do it. You can do it yourself without using that calculator algorithm as well. So if you do this, you get this as your 1.16, and because we have made sure that our forces were in newtons and the stresses were in MPa, so this has to be in millimeters. Now this is as far as the real FEM is concerned, in the sense that we transformed each element, which was basically for one element it's 1 minus 1 minus 1 1, A over L 1 minus 1 minus 1 1, that is just 2 by 2 plus. But when we convert this into global, then it becomes 4 by 4. So this was 4 by 4, this was 4 by 4. In the global system we added them together, we applied the forces, we applied boundary conditions, and we solved and we got the answers. Now we know all the things we needed to know. Now to calculate strains, because this question asks us to analyze the structure. Whenever a mechanical engineer is asked to analyze something, it means you need to find the strains and finally the stresses. So you, before going to that point to calculate strains, remember we told that we mentioned the fact that at this stage we have to go back to the global system, to the local system, because strains, stresses, these are local considerations. So we go back, and now it's very easy for us to go back because we have a formula with us which we derived, and that should be very handy to us now. And that formula was, if you recall, that was uv lm 0000 lm and here it was u ui uj ui naught vi naught uj naught vj. This is the formula I'm talking about. Please recall during our development for the K matrix, we started with this sort of a thing. There was 4 by 4 and then we took two things out. Please recall that. Now we have to use this for both our elements. Now we have two elements, so for element 1 this takes the shape. For element 1 this takes the shape, because for element 1 we have ui and u1 and u3. I'm sorry, for element 1 we have u2 and u3, so ui and uj become u2 u3. For element 1 we know L and M, so there's no problem here. 0.89 minus 0.4500 0.89 minus 0.45. And for element 1 the global had both these ui vi. For global we have vi's also, and then u2 v2 u3 v3. Now u2 v2 are 0. We only have to deal with these, so 0 0, and then u3 and v3 are as given here, minus 1.16. and if you solve this turns out to be 0 and 0.3. Now this 0 and 0.3, these are in the local systems. So we are, when we talk about this, then u, which is 0, is in this direction, u2 is in this, and u3 is in this direction, not in global system. And this is the direction in which we need the displacement to be, so that we can subtract this displacement from this displacement, both in this direction, and get the contract or stretch or whatever. For this, the displacement, the local one, will also be in this direction, because here the local and global coincide. So for element 2 you will have u1 and u3 now. Why? Because for element 2 this is u1 and u3, and the global ones will be u1 v1 and u3 v3. u1 v1 are obviously 0 again here. Now here we have 1 0 0 0 0 0 1 0 0 0. Here we'll have the same. Please verify, and we get 0. These are the local values of displacements. Both u's we're talking about. For this element, u3 u2. For this element, u3. Please see that both are u3, but one is in this direction, one is in that direction. So these are local ones. So these are not u3 knots. So now we are very close to finishing our problem, and all that remains now is using these values to find out the strains and then the stresses. So first the strains. Epsilon 1 is simply b ui uj. This is what epsilon, and obviously for element 1, ui uj means u2 and u3. u2 u3, and b for these problems is 1 over L minus 1 1. This is B matrix. u2 u3, you know, we have just calculated u2 and u3, 0 and 0.3. L for this problem, this will be element 1. So the first element had this length of 670.82, and this turns out to be 4.47 into 10 raised to power minus 4. Epsilon 2 similarly, b here it will be, for element 2 it will be u3 and u2, u3 and u1. I beg your pardon, this is u1, this one is u1, this one is u1, because here element, this is node 1, so u3 and u1, and u1 u3, and here we have this the values 1 over L minus B is matrix is the same, except the length, and here u1 and u3 you have u1 and u3, here you have 0 and minus 0.24. I'm talking about this one, u1 u3, here it's 0 and 0 minus 0.24. so this is what you have here. Here for L you have 600 now, because element 1 is 600. So if you solve this thing, you'll get minus 4 into 10 raised to the power minus 4. Obviously there's no unit for this, it's a dimensionless quantity. Sigma 1 is simply epsilon 1, Young's modulus 1, and epsilon 1 sigma 2, which this stiffness is the same for both, so it is 200 GPa, and if you use that you get, these are the final values. You can, and you should check this yourself, all the calculations. If there's something wrong, please give your feedback, and more importantly, do it in the right way. And obviously I'll also recommend that you should solve this and then solve it using some other method, for example mechanics of materials. It's very easy to confirm whether you're on the right track or not, so please do this. And now we take the another problem in which there is, and it will just, I won't solve it all the way, I'll just go through it and then tell you where you need to be different from the problem we just did. It's the same problem, similar problem, but you still need to calculate the strains and stresses. But here element 1 is subjected to a temperature change of minus 20 degrees centigrade. There's no temperature change in element 2, so in at least one of the elements you have to consider the force term. So in this case obviously you'll need to use this one also. The rest will be the same, but for one of the elements the thermal force vector will be calculated again in the global system, and at the end you will add this 20 kilonewton, and then you'll solve the problem after assembly, and after all the displacements have been found out you'll find the strains. But then before going to stresses you will subtract the thermal strain element from the strains to get the mechanical strains, and then use the Young's modulus to find the stresses. I'll just give you the solution for it, the answer for it, and leave the students to do it yourself. In this obviously u1, if I say this is, again this is element node 1, this is node 3, and this is node 2, then obviously u1 v1 and u2 v2 will be 0, so the u3 will be minus 0.225, and v3 will be 0.69. These are the values, the global displacement values. And if you calculate the strains and then the stresses, then sigma in element 1 will be 25 MPa. You have to verify this. And sigma in element 2 will be minus 15 MPa. Please do this and report that there's no problem with these answers. And if there's a problem, then that too please report. Thank you very much.